Our first workshop today will be presented by Shweta Singh, Sheeba Ransing, and Arushi Kapurwan. Shweta is a senior software engineer at Mathworks, and she is working in the product security space to ensure that Mathworks products and services are designed and implemented at the highest possible security standards. Sheeba is also a senior software engineer at Mathworks, and she's currently working on projects in the ROS toolbox, and her specialization is in the embedded system domain. And Arushi is the software development engineer at Mathworks in the Simscape product family. So she helps users model and simulate multi-domain physical systems using the Simlink environment. So Shweta, Sheeba, and Arushi will present the workshop Catching Fire, Autonomous Drones to Detect and Track Wildfires. Please welcome them.
Good morning again, everyone. As the slide says, we are going to present our workshop on catching fire. That is, we will use autonomous drones to detect and track wildfires. But before we get into detail, let us tell you a little bit more about ourselves. Myself, Shweta, as Julia mentioned, I'm working as a senior software engineer at Mathworks. One of the area of research for me is studying emerging behaviors in complex systems. So when I say complex systems, these comprises of autonomous agents, such as drones or UAVs, uncrewed aerial vehicles. Today, I will be introducing the workshop to you, and we will walk through exercise 1, where we will use the autonomous drones to solve a problem such as wildfire. Over to you, Arushi.
Thank you, Shweta. Hey, everyone. My name is Arushi. I'm a software development engineer at Mathworks. I'm basically responsible for creating user workflows and interfaces for Simscape family of products, which is nothing but a model-based design product for physical systems. And today in this workshop, I'll talk about catching fire using the object detection method. Over to you, Sheeba.
Hello, everyone. Good morning. I'm Sheeba Ransing. I'm a senior software engineer at Mathworks. My specialization is in embedded systems, and currently I'm working on robotic operating system development toolbox at Mathworks. I will be walking you through the exercise 3 or section 3 of this workshop. See you at section 3 then. Over to you, Shweta.
Thank you, Arushi and Sheeba. We also have a team of teaching assistants. We have Swati from India and Satya in the EST time zone, and all of us are in EST. I saw that there are multiple people all around the world, so welcome. And if you have any question or any point of time, feel free to put that in the chat. Feel free to use the Q&A for any specific questions, and we will be able to get to you with respect to what kind of a question you have. All right. So let's get started. Before we get into details, I want to start by asking all of you a question. How many of you can raise your hand using Zoom functionality, or just put a yes or no in the chat? How many of you have heard the term wildfire in, let's say, last couple of weeks or maybe a month? I'm gonna just give a, let's say there are a lot of raised hands here. We have a lot of chats too, right? I'm not surprised at all. It's not because it's such an easy term in our vocabulary to remember. It's because we are hearing this term again and again in the news these days. If you remember, in our childhood, we were taught that wildfires are used to renew the ecosystem for the forest. But recently, wildfires have become highly destructive. If we just look at the data in US itself, this year so far, we had close to 1,700 cases of wildfire just in the month of October, till from January to October. So clearly, it's affecting a lot of geographic areas. One of the main reasons for the cause is climate change. With the increase in average temperature all around the world, wildfire kind of an event is spreading to multiple areas, multiple geographic areas, leading to more and more forest degradation and damage to not just to the human lives, but to the wildlife itself. Now, if we look into the kind of methods that are there today to detect and suppress these wildfire, if we look back into more traditional approaches, there are watchtowers set up in the national park, for example, and where a person actually sits in those watchtower and look around in the area to find out wildfire-like situations. If we look at more advanced techniques, besides the heroic efforts of our first responders and firefighters, US National Forest Service have started employing low-flying aircraft in the region as well to detect and suppress these wildfire. Now, the problem with these solutions is that it puts human life in a considerable risk. So clearly, there is a need for finding a solution for this problem. Now, in today's world, we have a lot of technologies at our disposal. So the question that we can ask here today is how we leverage all these cutting-edge technologies to solve not just a real-world problem, but also a life-saving one as well. Today, we will be leveraging autonomous drones to create a solution for this problem. Why are we using drones? Because drones provide a capability to go into an area much closer than a human can do, so that it makes autonomous drone, usage of autonomous drone, much more relevant in this kind of a problem of wildfire. So let's consider a scenario. Let's see there is a drone which is flying over a wildfire-like situation, and it can capture the images using a camera, or it can capture a video file. It can send that kind of information in real time to control station, where a control station, a person is sitting to like control the drone maneuvering or movement around the area. Control station can send this kind of an information again in real time to a physical data store, or it can exist in somewhere in the cloud. And using the data analysis applications, we can perform fire detection in real time and also do burn analysis, that is to understand what kind of wildfire that existed in that particular area. So as I said, the drones can fly within very close range to the fires. They can detect fire while they are still relatively small. That enables human to monitor progress from a remote location and provide emergency communication channel to strong personnel at a remote site. So if fires are detected in very early stages, they are much easier to extinguish, with potential financial savings, millions of dollars from property values, and reducing firefighting cost as well. So that's exactly what we're going to do today. We will build a solution in 3 incremental exercises. We will look at exercise 1, where we will use a simulated version of the drone and apply an obstacle avoidance to maneuver the drone in a forest-like situation to see how they avoid the obstacle and move from one point to another. In exercise 2, Arushi will create a scenario where we will use the information provided by the drone to do fire detection. And in exercise 3, Sheeba will walk you through how can we go one level deep to understand the burn analysis using hyperspectral images. So through this exercise, we will see how accessible these technologies are to use to create such a solution with handful of steps. And by the end of the exercise, you will be comfortable using them to think of various solutions for not just to the wildfire-like situation, but any other real-world problems as well. All right. So today we will be using Matlab Online, which is our programmatic version of the desktop Matlab. In Matlab Online, we will use multiple toolboxes. For example, UAV toolbox for first exercise. We will use computer vision for second exercise and image processing in the third exercise. And we will leverage Simulink Online as well, which runs on Matlab Online. So if you have not done the pre-work yet, I would advise you to go to this link, start creating the Mathworks account and get access to the files. So once we are ready to do the exercise, you are all set up and we don't invest time in doing the pre-work. All right. And if you have any question, just shout out to our TAs and they're here to help you for any problem that you might have completing the pre-work. All right. So let's go into our part 1, which is obstacle avoidance. What we will do here is we will simulate a drone flight using obstacle avoidance algorithm. So because we are in a wildfire-like situation, we will create this scenario of our own where we have obstacles as trees, and we will make sure that the drone is moving from one point to other. These points are called waypoints, and we will provide these waypoints as well for the drones. So first position will be start position, and drone will move around from one waypoint to other, making sure that they are not hitting any obstacle. The question that you can think of here is like, why am I thinking about obstacle avoidance or waypoints? So you can think in terms of, for example, first responders can be close to an outbreak, and you can point out those as a waypoint, as an interest point. Or you might know that there are specific events like lightning strike that are point of interest. So you can put that as an interest point or waypoints for a drone to travel and see what kind of information that they can get from the scenario. Or there is a possibility that there are transmission points where there is a high likelihood of being fire. So in those cases, all of this waypoints will be helpful for a drone to know in order to maneuver its path through the obstacle. All right. So let's meet our drone. Obviously, because we are in a virtual environment today, we will be using a drone in the simulation environment. For the purpose of our application, we will use a quadcopter. So if I go back to a definition of drone, a drone can be any vehicle that moves on air, water, or land. But for the application for the wildfire, we want a drone that flies. So we will use a quadcopter, which has 4 rotors attached to it. There are 2 main features or attributes associated with this drone. We will consider sensors. So sensors can be anything which is mounted on the drone itself. For example, we can have air pressure sensors that stabilizes the altitude and allow a drone to hover over a particular area to allow it to take like pictures or videos. Other examples of sensors can include like LiDAR, which is one of the very popular ones used in like self-driving cars as well these days, or accelerometer or gyroscope or barometric pressure sensors as well. Another feature or attribute that we will use is remote sensing. Remote sensing is about detecting and monitoring the physical characteristics of an area by measuring its reflected and emitted radiation at a distance. For example, if you use a LiDAR sensor, it will send a laser light and understand what physical attributes are in this area to make their decision based on its control and the environment and state of that drone. Before we get into detail, let's get into some of the navigation assumptions that we will consider in the exercise. We will have a single quadcopter. We will have only the static obstacles, that no moving obstacles. So we'll have a static environment. We will have a LiDAR as a sensor on our drone. A LiDAR stands for light detection and ranging, sensor to navigate the space. We will consider the fixed waypoints, that is interest points, to move towards. And we will use an algorithm called a 3D vector field histogram, where what this algorithm will do, it takes the inputs such as space, start positioning, the goal position, and the obstacle in the scenario. For the operation, drone will use its LiDAR sensor to find the next possible available free point in the path as is explored the space. And the output would be finding an optimal path with an obstacle avoidance through all the waypoints. All right, so let's review step by step. So I hope you already completed the pre-work by now, but let me go through each step that we will be doing in the exercise 1. Setting up the exercise, we will run the catching fire _ setup in the command window once you have access to Matlab online on your browser. Catching fire setup, the script will add essential folders in your path and also open Simulink online in the background so that once you are ready to run the exercise, it's very quick for you. First step for obstacle avoidance, we will create a scenario because we are in a forest-like situation. So this, once you type exercise 1 _ step 1, this will open up an app for you that will allow you to add obstacle and the waypoints and create a scenario. And once you are done, you will type exercise1_step2 to open a Simulink model that allow the drone to move around the created scenario. And if you are ready to do the pre-work, I would advise you to type this right away so that once we are in the exercise for 5 minutes, we will do the rest of the steps as well. While you're doing it, while the Simulink Online is opening in the background, let's look at what exercise step 1 is going to do for you. This will open up an app like this. It will be on your screen in your browser. And there is a middle plot that you will be accessing. So for first step, you will click on the add trees. That is, you'll click anywhere in the plot in the middle, and wherever you click, this will add obstacle in your scenario. Step 2 would be adding the waypoints. In waypoints, you will click somewhere between the obstacle to provide an input to the scenario where you are saying that start from the first position and then move towards the added waypoints. And once you are done, just click on create the scenario and it will pop up a plot such as this where it will add obstacle as trees. The red circular ones are the waypoints, and the blue one is the first waypoint that you added, which will act as a starting position for the drone. Step 2 will open up a Simulink model for you that will actually take the scenario and runs the drone. So what this it looks like complex, but nothing to worry about. This is already pre-done for you. What it's doing it divides the model into multiple components. First is a scenario building. That is the scenario that we built. It gives it to a drone. It builds a scenario for it. Second is a control panel where you can change the look ahead distance of a drone to see what could be possible in the vision range. Third is the waypoint following and obstacle avoidance. That is actually the implementation of the algorithm, the 3D VFH. And in the fourth one is based on where the drone is at the moment, it will control the position of the drone. And once you type exercise1_step2, this will open a model scenario where a drone will be moving towards the within the obstacle, trying to avoid it and move from one waypoint to another. All right, I think we are all ready to run the exercises. So we will have 5 minutes for you to run the exercise. Please remember, if you have still not done the pre-work, feel free to do that quickly. We'll have to run the catching fire setup, type exercise1_step1, and then once scenario is ready, we'll do exercise1_step2. If you are done with both these steps, update the parameters and rerun the exercise to see what happens. So let's take 5 minutes to complete this, and we will start with the presentation once we are done with the exercise 1. Feel free to add any questions in the chat if you have any. Remember, once you are on step 2, that might take a little bit of time to open up Simulink Online, but it should be quick. But if you are having any errors in the command window, feel free to let us know what kind of errors there are. And if you're done early, let us know that too. It means we are successful. Doesn't look like there is some action going on. We have a question. How can we pop up the first table? Are you mentioning about the app? Then it's exercise1_step1. So once you are done with the pre-work, type catching fire_setup to add all the essential folders and the scripts on your environment. And this will open a Simulink model in the background. Exercise1_step1 will open up the app, which will allow you to create scenario by yourself. Has anyone able to successfully run step 1? Looks like there are a few errors that we're getting. Hopefully those are resolved soon. All right, I guess there were a few people. I saw a thumbs up for step 1. Let's see if you are able to run step 2. There is no interaction in step 2, but there is a possibility that in runtime, you can change the look ahead distance and see how drone is reacting. Think about what parameters that you can change to see a different kind of a path. All right, I think my timer did stop a bit, but we will take into consideration that. Please note that you will have access to these files if in the remaining time you are not able to complete the exercise, that's fine. You can do them offline as well. But we will be in touch if you're still getting any errors. All right, we'll give 1 more minute because I think the timer stopped in between. Looks like there is a bracket in the URL when you are unzipping. So make sure that that bracket is not there. And we have a good question about the implementation of the connectivity and coverage. It depends on the type of drone we are using. It can be on 5G. Wi-Fi will limit which the area you are in, depending on how much coverage is provided for it. All right, I think we believe we can restart our presentation and hope people are able to get through the exercise in the offline access to the exercises. So let's summarize it. So we were able to create a scenario, and hopefully we are able to run the drone as well through the obstacle. So the question that we can ask ourselves right now is that, can you change the trajectory of the drone by updating the waypoints? Like if you make waypoints very close to the obstacle, how drone reacts in those situations? And what other parameter besides changing the waypoints we could change for a drone to have a different kind of a path? All right, so what is next? How are we gonna put our pieces of puzzles together? We are talking about creating a solution for wildfire detection. So what is the next steps? So we use a LiDAR sensor on a drone to move around in the area and avoid the obstacle in that scenario. They can be multiple kind of a sensor attached to the drone to get different kind of information. For example, we can have a RGB or a multispectral camera on the drone itself to get different kind of information, for example, images of an area in RGB format. And based on that information, we can create our own application, own algorithms, and analyze the data to get valuable information. And that's what Arushi will be going through to do fire detection. Over to you, Arushi.
Thank you, Shweta. Let me just go ahead and share my screen.
Thank you.
All right, can you see my screen? Okay, awesome, thank you. Hey everyone, this is Arushi, and in this next section, I'm basically going to talk about catching fire or instances of fire from the RGB images using object detection. So to recap, in part one, you deployed your drone in a simulated environment and demonstrated how to use data from LiDAR sensors to try and navigate around obstacles in that environment. However, as Shweta mentioned, we might also want to consider other sensors for general data collection purposes and analyze that data from a safe distance away from the wildfire. In this section 2, we're going to talk about what you can do with the sensor data that the drone has collected with the help of a RGB mounted camera. You'll try to spot fire in a live stream of images and accomplish object detection. Now, before jumping into the task of object detection, let's take a step back and understand what detection is. What exactly do we mean by it? And to answer that question, let's break down detection into two tasks. First, finding the bounding boxes, or finding the location of the objects within an image. And second, classifying them or applying labels to them. So let me explain this concept with the help of an example. Here you'll see that there is an image and we have an object that we have wrapped in a yellow bounding box that identifies the location of the object in this entire image. And then we apply a label vehicle to classify the object as a vehicle. The models that perform this type of task are called object detectors, and that is what we'll be using in exercise 2. Now, one common class of object detectors is called YOLO, which stands for You Only Look Once. There are many different versions of it built on a common architecture, and the version that we'll be using today in this workshop is called YOLO V3. Now, why exactly is YOLO good for object detection in our case, that is catching fire? Like the name suggests, YOLO is a single stage detector, meaning it kind of determines the bounding boxes for location of object in an image and classifies these objects directly in one stage. So not all of the detectors are able to accomplish these two tasks in one stage. These other two-stage detectors basically find the region of interest in the first stage, and then in the second stage, they determine the bounding boxes and the labels. YOLO being a single stage detector is very impressive in terms of speed at which it can run and serves advantages over other types of detectors, especially when you would like to perform detection on a real-time data. For example, like a real-time video stream coming from a camera-mounted drone. Now, the images from the mounted camera are true color images or RGB images. And the data in these RGB images are nothing but matrices. So if you look into the image on the right, you'll see that each pixel in that image has a red component, green component, and a blue component, which are nothing but the three color channels of the data. So our network, that is YOLO V3, and many of the popular mainstream object detectors are trained on this RGB data. So what happens when we pass an RGB image from our drone into this network? It undergoes a process of transformation, and the goal of that transformation is basically to reduce this high resolution image data into just core features, which are aspects of the data, helping us to distinguish between objects. For example, in this network, you'll see that there is an RGB image of a sailboat, and in its intermediate layers, it will reduce that information from the RGB images down to just a set of edges. And then that lower resolution information, which was once used to locate the objects, in a decoding step, can be mapped back into the original image to identify where the bounding boxes are for each of the objects that we are detecting. So depending upon the type of the data that you're using, RGB data or something else, the features that are extracted by this network may look different. And the good thing is that you'll get a chance to explore the output of these intermediate layers in exercise 2. You'll get to know exactly what a model sees when it tries to perform detection. All right, so as I mentioned before, in exercise 2, you'll be using YOLO V3 to detect instances of fire in RGB images. And for today's workshop, we have provided you with a pre-trained model that has been fine-tuned for this task. All right, but let's get to know our model before we actually start running it. One way to characterize the model is through model cards. They are nothing but the product specifications of a machine learning model. They describe the technical details of the model, like how it was created, what is its scope, what are the technical limitations, as well as the information about the ethical considerations and any risks involved in its creation or use. Now, all of these factors are very crucial in understanding and documenting how a model might behave in a real world. So for the model that you'll use today, that was purely built for educational purposes, but you'll soon see that we can get a feel of how this model might actually behave in the real world by looking at some of the information on this model card. Now let's specifically think and talk about ethical considerations and the caveats of using this model. So as I mentioned in my previous slide, the purpose of this model is purely educational. And in the real world, if you were to deploy a drone using this model to detect fire, it could pose significant risks to you and potentially to other people. So let me point out by saying that the US Forest Service does not want you to deploy drones to active wildfire regions, as it might pose risks to you as well as to first responders working in these wildlife regions. So bottom line on top, we don't encourage you to use this model in the real world as it's not safe. Now, the other thing I do want to talk about is the data. What kind of data was used to train this model? So keep in mind that we fine-tuned this model using a small sample size of RGB images. And that is not necessarily representative of the types of wildfire that you'll see in different regions around the world. This data is not representative of all of the scenarios in which a fire can occur. It's also important to think about the fact that what if the model does not detect fire in a region where there is one? That again poses significant risks and problems. Therefore, we need to think about all of these different scenarios while using a model and how it might be risky in the real world. All right, so we went through a bunch of concepts like object detectors, YOLO V3, RGB images, model cards, and so on. So let's use that knowledge and apply it in exercise 2. So you'll kick off the exercise by hand labeling the bounding box in the image that we have provided. And you, the expert, will say that here is an instance of fire in an image. Now, in the next section of exercise 2, you'll use a pre-trained YOLO V3 object detector to predict the bounding boxes and assign the label fire to it, along with a score of how confident the model is in that prediction. Then in section 3, you'll have a chance to evaluate the model's accuracy by comparing the model's results to your ground truth, which was the hand labeled bounding box you did in step 1. All right, so it's time for exercise 2. Let's switch back to Matlab Online and navigate to exercise 2_detectfire.mlx file. So you'll start by labeling the image that we have provided. You'll predict the bounding boxes of the model. You'll evaluate the model's accuracy. And then in the last couple of sections, you can explore the intermediate layers to see what exactly the network is seeing when it analyzes this RGB image. And again, feel free to post any questions that you have in the chat. Our wonderful TAs will help you during this process. So Let me start the timer. So just to reiterate, navigate to exercise2_detectfire.mlx file, and then you can run exercise2 using that file. Thank you, Swati, for posting the direct link for all the resources for exercise 2. Once you've completed the exercise, feel free to post the overlap ratio that you were getting. Was it like a good overlap ratio or a bad? Feel free to post that in the chat. And then we'll discuss about some of the factors why you have gotten a lower overlap ratio than expected in the next slide. Pallavi, I'll answer your question after I have kind of summarized my thoughts on the next slide, and then I'll answer your question. Thank you for your patience. I'm not seeing any numbers in the chat so far on the overlap ratio. So if you're running into any issues while running exercise 2, please post them on the chat. And it's okay if you were not able to run the entire exercise. We are going to provide you with these files even after the workshop. We are getting some error while running the model yellow V3. Could you please post the entire error message? I believe, make sure that you do the step 1, which is labeling your ground truth, and then closing that figure after you've drawn the bounding boxes for the instance of fire. But I think our TAs will kind of figure out why you're getting this error. All right, I think I'll go, I'll kind of reconvene and start with the next slide because we're almost done with exercise 2. So, all right. So let me just, in the next slide, just kind of recap the results that we have been getting from running exercise from running exercise 2. So for those for those of you who were able to finish the exercise 2, you probably would have noticed that that the model would have struggled with the sample image that we have provided by showing a lower overlap ratio than expected. So you might be curious to know why did that happen? Why did not my model correctly predict the instance of the fire that you have kind of labeled as the ground truth? And to answer that question, we do need to think about the model card of the model that we were using today, and specifically focus on some of the potential caveats of using this model. So one thing we might consider is that the data is not well represented in the original images that were used to train this network. Maybe it was the factors like lighting or the background that doesn't match with the training data, or even the instances of fire doesn't look the same. Or there could be some fundamental problems like, what if the fire is obstructed by smoke? Will the model be able to detect where exactly the outbreak is occurring if we didn't have a good visibility to begin with? Probably not. This type of problem might not be surmountable with the type of data that we are using and the way with which we have set up the problem. So using RGB images from a visible light spectrum won't help us in detecting fire when there's smoke. Maybe this means that we need to consider a different type of data that will give us more information to analyze where the fire has happened. This leads us to our next section where my teammate Sheeba will show us how exactly to do that and perform burn analysis using hyperspectral images. Over to you, Sheeba.
Thank you. Let me share the screen. Sure. Sorry. Let me know if you're able to see this, see the presentation.
We can see.
Okay. Thank you. Thank you, Arushi and Shweta, for showing us how we can use drones to fly over the remote area and detect the fire using technologies like deep learning. We are hoping to see some drones flying today after this workshop. Good morning, everyone. Welcome to the third section of this workshop, that is burn analysis. In this section, we will try to see what is the advantage of burn analysis, what are the techniques that we are using for this analysis, and how Matlab is going to help us to solve this problem. Why burn analysis? So by flying the drone over the potential fire zone, we have collected different data from the sensors and we have detected the fire. What next? Can we get some answers from this sensor data, like what caused the fire, where it was originated, and can we detect the state of the vegetation after fire? Can we detect if we can regrow the vegetation, and we even detect the soil fertility and so on? The answer to these questions are yes, and it's possible using hyperspectral imaging captured from the hyperspectral cameras that are mounted on the drones. What is hyperspectral imaging? A human eye or a regular camera can capture the light from visible light spectrum. But why are we talking about lights and spectrum when we are doing burn analysis, right? Let's take a step back to refresh. We know that in order to identify the behavior of a material, we need to understand how the material interacts with light. When a light falls on an object, it either reflects or refracts from the material. We capture these reflected lights and compare it with the spectral signature to identify the material or to understand the health of that material. Coming back to my previous point, human eye and a regular camera can capture the visible light spectrum reflected from these materials. However, these materials will also emit some different bands of spectrum, that is infrared, ultraviolet. These are called hyperspectrum. There are devices called hyperspectral cameras, which are used to capture these wavelengths of light, and the images obtained from these devices will help us to understand and visualize the behavior of this material. So hyperspectral imaging measures the spatial and spectral characteristics of the object by imaging it at different wavelength. The data that is obtained from this images is a 3D array. It's in the form of M by N by C matrix, where M and N are the spatial information and C is the spectral dimension. The 3D array, this 3D array is called a hypercube or a data cube. From the image on the left side of the screen, you see we have a 3D data cube. Let's consider a small portion of it, say vegetation. A 2D image of this portion will be as is, like you will see a green vegetation in a RGB image. But when you consider a 3D image or a 3D data cube, this contains more information of different wavelength which was captured, and it gives us different properties from that scene. So it tells us about the color, it tells us about what all the materials that are available, like for example, is there a soil, is there moisture, is there presence of water vapor, and type of vegetations, etc. Hence, a 3D data gives us more, 3D data cube gives us more information of the scene. Now that we have understanding of what hyperspectral imaging is, we will try to learn more how this is used for burn analysis with the help of an exercise. The format of this section is slightly different than what we did in section 1 and 2. In this section, we will work on the exercise together. You can, once you download the project folder, you should be able to navigate to the exercise 3 folder, and you'll find an MLX file in this folder. You can open the MLX file by either double clicking on it, or you can just type edit and the file name. Once the exercise is loaded, this has different sections. First 3 section is exercise 3.1, and then exercise 3.2. Then you scroll down, you'll find 3.3 and 3.4, and then you'll have take home as 3.5. When we are running the exercise, you can either run from the run button in the tool strip. You can either run or use run section to run a particular section of this script. Let's go to 3.1. I hope everyone is with me. Just a thumbs up or something, raise hand if you are able to open this file so that we can move to the exercise 3.1. Let's go to section 3.1. So in this section, we'll try to learn to work on the hypercube data. So for this exercise, we have shared with you three different images as a test data. One is the open field in Indian Pine Ridge. Second is a campus of Pavia University, and the last one is the mountain range where the wildfire happened in the nearest past. In this exercise, we will first load the data in the workspace, and then with the help of an image slicer function, we will be able to figure out each one of the wavelength that the image is located at. When we select an RGB image, you should be able to construct a true color image. And when we select any other band other than RGB, you will be able to construct the false color image. When we know that the leaves emit infrared, so using CIR, we can emphasize on the leaves as red in this case. So once you run this exercise, you should be able to see these outputs. I hope everyone was able to get the expected results. If you need any help, please feel free to add your questions in the chat. One of our TAs will help you. Moving on to next exercise, exercise 3.2. Now that we are familiar on how to use hyperspectral data cube, we will try to understand and identify different regions in our hyperspectral images by performing abundance classification. So every image is made up of pixels, and each pixel is either a pure pixel or a mixed pixel. When I say pure pixel, it means it has single spectrum, or when I say mixed pixel, it means it has two or more spectrum. Also, we know that every material has their own spectral signature. It's similar like a fingerprint of that material. So these spectral signatures are defined in the EcoStress spectral library. Using this library, and we will try to identify the different regions in our image. So in this exercise, let's take a data sample from Pavia University data set. This data set, you should be able to identify 9 regions, like asphalt, meadows, gravel, trees, etc. So what we are doing is we'll take a hypercube data, we'll take a pixel from the hypercube data, we'll map we'll calculate the abundance classification of that pixel, and we'll map it with the end member signature, that is spectral signature. So for example, if you want to identify the asphalt in the image, you can just map it with its spectral signature, and you should able to find where the asphalts are in your hyperspectral image, or where the trees are located. So when we do this activity to all the 9 images, you should be able to identify all the 9 images in your image, in your data. So I hope you were able to get to this output. Moving on to next exercise. Now that we have identified different regions in the image, we will try to dig deeper into one of the region, that is the vegetation. So can we will try to identify the type of vegetation that is available using the interactive thresholding of NDVI map. NDVI map indicates the density of vegetation in various regions of hyperspectral data. The NDVI map is computed using near infrared and red spectral band of image from a hyperspectral data cube. The pixel in the region with healthy data, healthy vegetation or a dense vegetation will reflect more NIR light, resulting in high value of NDVI. The pixel where there is like unhealthy or a barren land will have low NIR land, absorbs more NIR light, resulting in low NDVI value. Based on this information, we can identify different regions in our image. So let's consider RGB image of our of a data cube, and for each pixel, let's calculate the NDVI map. So based on this information, we should be able to identify where there is densely vegetated versus where there is no vegetation at all. So for example, if you consider this small portion here, it looks like a metal, and when you see the NDVI map here, it says there is no vegetation in this region. Whereas if you see this here, you have high vegetation. So when you plot it for further, you can highlight the region where there are high vegetation. Moving on to exercise 3.4. Here, now, in a similar way, the way we identified different vegetation in the image, we would try to identify the severity of burn. And here in this case, here we will be using normalized burn ratio, NBR. The NBR is calculated using NIR and shortwave infrared. The high NIR indicates that there is a high severity, and the low NBR, sorry, high NBR value indicates high vegetation, while low value indicates the bare land or recently burnt. NBR area are normally attributed when it is equal to 0, it means that there was no burn in this area. So like what we did in the previous section in 3.3, we will pick up the RGB image and we will calculate the NBR value for each pixel and determine the area where there is high severe burn and all versus there is presence of water. We can even identify if there is a possibility of the regrowth of vegetation after the burn. So you can see that here, like marked in a light blue. So all that we did here is we captured the hyperspectral data after the burn has happened. Using the hyperspectral data over the time, like before the burn, after the burn, and while the burn, we can even get more information, like where the burn has originated, what is the cause of the fire breakout. We can identify the climatic condition which resulted in this fire, and we can even predict if the vegetation can be regrown in the affected area. And all that we have to do is to get the hyperspectral sensor data and then represent it in the form of 3D metrics and filter or pre-process the data and interpret the data accordingly. We can also use, here we will use AI technology and convolution neural network to train this model with different data that we have collected over time and predict the regrowth possibility or predict the any wildfire in future. You can take this model and all the required data that is shared with you with this exercise as a take home and try it out. We would love to, we would like to see you tweaking the different parameters. You can check how the model behaves. And if you have any questions or if you need any help, please write to us. We will be more than happy to help you. So this is end of our section 3. I hope everyone was able to get the results, get the script running. What we have learned today, can we apply? We can apply this in this in different fields, like in the field of study the climatic changes to detect the melting of the ice. We can use this in the field of medicine to identify the tumors or any abnormal behavior of the body parts. We can also use in the field of farming where we can identify and fix the defective crops in very early stage of farming. I hope you would be using today's learning in your area of study. We would be looking forward to hear some exciting research stories where you have used this Matlab along with Matlab and Simulink to solve the problems. Thank you, Wits, for giving us this platform to showcase how Matlab and Simulink is used today. Thank you, everyone, for being a wonderful audience and taking your time and attending this workshop. Feel free to write to us on LinkedIn if you have any questions on how to use the product, how to use the tools. We will be more than happy to help you. Thank you so much.